Hey everybody, it's Mr. Bradley. Today I'm going to give you about a 15 to 20-minute lecture about different wave behaviors. I want to talk to you about four things that waves do. These are important wave behaviors that we will be making use of over the next few weeks as we look at sound and light waves and water waves and lots of different things, right? So these are kind of important ideas. I'm going to use the note slides that are available on Google Classroom. I'm not going to talk about each one of them specifically. More than anything, I'm just going to talk about the main ideas and I'll give you a couple demos, and then I'm going to give you some time to learn about these things on your own. All right, so let's get started. The first wave behavior that we're going to talk about is something called interference, right? So interference is simply the idea that when two waves meet each other in the same place at the same time, they're going to interfere. Waves are either going to add together or they're going to subtract. When waves add together, we call that constructive interference, right? This little illustration right here kind of gives you an idea of what constructive interference might look like. Let's say you had two wave crests right here that were coming to meet each other. When they get to the same place at the same time, the wave is actually going to be higher at that point than it was before, right? Because the two waves add together. The next kind of wave that we would see is, or the next kind of interference that we would see is destructive interference. Destructive interference is what happens when waves cancel out. So it's almost like you have the high part of one wave hitting the low part of another wave, and there could be a moment in time right in the middle where they completely cancel each other, right? That's called destructive interference. Let me show you like a little quick simulation that will kind of give you an idea of what this looks like. Okay, so when I go to this OPhysics website, it's kind of cool because it gives you a good way of being able to see how all this stuff works. And so what I can do is basically have these two waves going towards each other. So right now I've got like a positive wave there, and I've got another wave that's positive as well. The second wave here is actually taller than the first wave. And what I want you to notice is that when I let those waves go towards each other, you can see they actually end up, adding together. If I can pause it in just the right place, like right there, I almost get complete addition. The one wave, which is illustrated in red right here, is adding together with the wave that is blue, right? So there's the red wave, there's the blue wave, and as they add together, you can see you really get like this net wave right here. So that's constructive interference, okay? Destructive interference is what it looks like when you have a tall wave and a short wave meeting each other. So I guess the better terminology here would be a crest and a trough, right? So I have a crest on one side, I have a trough on the other side, and as they just continue to go back and forth like this and meet each other, there's going to be a place in the middle where they completely cancel. If I could pause it just in the right place, which I can't. I wish they had a frame by frame on this, but they don't, right? But if you can imagine just, boom, actually, I can frame forward with time right here. Well, they don't get complete cancellation because the waves aren't the exact same height, right? If I made both of them the exact same height and I kind of drag this slider into just the right place, boom, you get complete cancellation, right? But any other time, those two waves exist. There's really just that moment in time where they completely cancel each other out, right? Which is pretty cool. Pretty cool. That's the concept of interference, okay? Oftentimes interference is going to be way more complex than that, right? Like this slide just shows you all the different times where interference can be far more complex than what I showed you there. I can go back to the same simulation that I just showed you, and I can show much more complex interference down below, right? And this simulation right here just kind of shows you, basically what it's going to look like when more than one wave pulse meets in the same place at the same time. You're going to get places of constructive interference. You're going to get places of destructive interference. Okay. All right. So back now to this. I think that's all I want to talk about with interference right now. As long as you understand the idea that there's constructive interference and there's destructive interference, that's what really matters. Okay. So the next thing I want to do is I want to talk about something called reflection. Okay. Reflection is actually a very, very basic concept. Reflection occurs whenever a wave strikes a barrier and bounces back into the medium that it came from. Okay. The illustrations that you're looking at right here probably don't really make a lot of sense. If I show you this little simulation, though, I think this will help to make the whole thing kind of make sense. So first of all, let me explain to you what it is that you're going to see right here. Okay. And this is meant to be like a tank of water. So I want you to imagine that you have a tank of water that you can make waves in, and you're looking down on the top of the tank of water, and you're seeing waves that are moving through the water. Okay. What you're looking at right here in particular is a place where waves could be created right here. Okay. And this little region is where you're just going to get a very simple wave be created. That wave is going to move down and up because waves move in all directions, right? So that wave's going to move down, and the wave that moves down is going to hit this barrier that you see down below right here. Okay, so I've got a barrier right here, and the wave that moves down is going to hit that barrier, and it's going to reflect off. What we want to do is we want to see what's going to happen when it reflects. Okay, so when I go ahead and let this simulation run, you can see the reflection that occurs. Here's the key thing that I really want you to get out of this right now. I want you to be able to look at the wave that's coming in and the wave that's going out and see how they compare to each other. So what I'm going to do is I'm going to stop this in a very specific place. I'm going to stop it right there. Okay. And actually, let's let it go a little bit farther. Right there. Okay. And then what we can do is we can draw some arrows that represent the wave that's coming in and the wave that's going out, right? So this is the wave that's coming in right here. Okay. That's the wave that's going to strike the barrier. This is the wave that's reflecting. Okay. If you look at that illustration, you can kind of tell that the angle that the wave is coming in at is the same as the angle that it's reflecting at. If you like measured that angle there, and if you measured this angle here, you can tell that those two angles are the same, right? This is just called the law of reflection. The law of reflection is maybe one of the simplest things that we'll learn in this whole unit, which basically just says that the angle of incidence equals the angle of reflection. I would say you're fairly familiar with the law of reflection because if you've ever bounced a ball on the ground, whether it's a basketball or a volleyball or a tennis ball or any kind of ball, a bouncy rubber ball, you know the law of reflection. Like, you know that when you throw it at the ground, it's going to bounce off at the same angle that you threw it at. It doesn't bounce back at you. It bounces forward, but at the same angle. Okay. So anyway, that's kind of the concept here with what reflection looks like. Okay. There's going to be a lot more for you to learn about with reflection in the future, but that's the key thing of what I wanted you to see for right now. Okay. One thing I do want to point out about reflection is that we tend to reflect waves off of curved surfaces quite often. Oftentimes we'll reflect them off of parabolic surfaces. In the situation of like a satellite dish, say, this would be what I would use for my satellite dish reflection right here. And, the whole idea is that you have a whole bunch of waves that are coming in from the left, like so. And those waves are reflecting off this curved surface, and they all focus to this place right here. That place is called a focal point, right? Which makes a lot of sense. So we'll see a lot of curved reflections and how those things are important in some activities that we will do later. All right. So now the third wave behavior I want to talk to you about, it's called refraction. Refraction is a new concept for you, I would think. The definition of refraction is the fact that waves will change speed when they're entering a new medium. Now, what I mean by medium is the material that the wave travels through. Okay, let's say you were thinking about sound traveling through the air. The air is the medium that carries the sound. If that sound goes into a different material, it's going to change speed, right? Most oftentimes it's going to slow down. Like, for instance, when sound goes from air into water, it's going to slow down. Okay. Oftentimes when they go into different mediums, they'll slow down. But sometimes things might start in a slow medium already, and then they'll actually speed up when that happens. Okay. Now, the way that ends up playing out is that you see a change in the wavelength when that happens. So what I want to do is I want to go back to another simulation with a wave tank. and I want to kind of show you what refraction is going to look like. Okay. So what I'm going to have here is I'm going to have some waves that are originating up here in this kind of green region right here, right? And these waves are going to move down towards this surface. And then I want you to imagine that it's just going into a material that's actually slower. So this medium down here is actually like a slower medium. So you're going to see what happens when the waves slow down, okay? What I want to do is I want to change the brightness of this simulation a little bit so you can see like the waves a little bit better. And now we're going to go ahead and let this go. We're going to let this run, okay? So notice what happens when those waves that were starting in the upper medium go into the lower medium. You can see that they still continue to move forward, and I think you can tell that they're definitely going slower, but not only that, they're closer together, right? Let me stop this. Let me stop the simulation in a good spot, right? And you can compare the wavelength here to what the wavelength there was. By the way, the ones that I circled on top, those are actually reflected waves, right? When you watch this simulation, you can see that some of the waves don't actually go into the new medium. Some of the waves actually bounce off and they go back into the medium that they came from. Okay, so you can see the ones that are bounced back have the same wavelength they had before, but you can see the ones that go into the new medium, they're actually closer together. That's what happens, right? When waves go from a fast medium to a slow medium, the wavelengths get closer together. When they go from a slow medium to a fast medium, the wavelengths get farther apart. Okay, all right, so that's basically what the basics of refraction are. What happens when waves hit at an angle, like in this picture? Well, not only do the wavelengths get closer together, but the waves actually change direction too, right? So to show you this one, I'm going to just open up a different simulation that'll still allow us to see what it is we want to see. I'm going to go to the PhET website where they have this simulation where you can basically like shine light into water, okay? We're going to go ahead and represent this light as though it's a wave, and I'm going to turn it on so that this red light is like hitting on a surface and essentially bouncing off the surface right there, although some of the light goes into the new medium. The way this whole thing is set up right now is that the new medium that it's going into is water. So this would almost be like if I took a laser and tried to shine it from air into like a swimming pool or something like that. Well, you can notice that what happens, not only does the wave get closer together, right? Not only does the wavelength get closer together, but also you can see that it changes direction at the same time. Okay. So if I pause that, you can kind of get the idea that these waves right here are closer together than they were up there. Also, it's changed direction. It was trying to move in this direction, but it ended up kind of bending down towards that dashed line when that happened. Okay. If I kind of change the angle that this is at, you can see that it bends even more. And also you can probably tell that less of it is transmitted and more of it is reflected. When lights hit at a big steep angle like that, or when any wave hits at a big steep angle like that, more of it's going to be reflected and less of it's going to be transmitted. Okay. So anyway, this whole thing really illustrates the concept of refraction. Okay. Okay. So our last example that we're going to look at is something called diffraction. Diffraction is totally a cool thing that waves do, and this is a really important behavior that explains a lot of things that all of waves do, but especially sound and light. So the definition of what diffraction is basically the idea that it's the spreading of waves around the edge of a barrier. Whenever waves hit a barrier, something that's in their way, they'll actually spread around it when that happens. So in this simulation that I'm showing you right here, this is the barrier. Okay. It's actually like yellow on the simulation, but I'm going to color it in pink right there. So you have these waves that were coming from the top of the screen and they hit that barrier and they bend around the barrier. And this area, the waves that make it around the barrier, that's called the shadow zone, right? And if you've ever looked at like a shadow and you've noticed that there's like fuzzy edges to the shadow, it's because of diffraction. That's why that's happening. Okay. So anyway, let me go ahead and open up a simulation here to show you what this looks like. Okay. And again, I'm going to go ahead and stop this and clear it like right before everything happens. The two barriers that we're looking at, right? One of the barriers is right here, and one of the barriers is right there. Okay. And I'm going to have some waves coming from the top of the screen. And what ends up happening with this simulation is that when the waves, hit both barriers, it's almost like they're going through an opening. You can see that the waves spread out, right? Now, here's the super key thing about all this, and we're going to see a lot of this over the course of this unit. Not only do the waves spread out, but there starts to be some places where you can see there's like a really strong wave right here. And then you can see another place where there's kind of like a weak wave. There's a weak wave there, and there's a weak wave there, and there's a weakness, and there's a weakness. Those yellow lines that I marked are places where the wave is kind of weak. Well, this is a really, really important thing. We're going to see this happen with light. We're going to see it happen with sound. But this is like a combination of diffraction and interference happening at the same time, right? And when that happens, really cool things happen. Okay, so anyway, you're seeing kind of diffraction in an example. And that the way I would really want to define diffraction again is just simply the spreading of waves around the edge of a barrier. Okay, that's what diffraction is. One thing I'd want to make sure that you know is that the relationship between wavelength and diffraction, waves that are closer together don't diffract as much. Waves that are farther apart, they diffract more. So longer wavelength waves have a higher diffraction. Lower wavelength waves have a lower diffraction. And then also the size of the opening matters. If you send a wave through a really wide opening, there's really not going to be very much diffraction. But if you send a wave through a very narrow opening, there's going to be much more diffraction. All right. I don't know. There's all kinds of little other pictures in here to kind of show you some examples of diffraction. I thought I had one more, but I don't have it. But these are things that I'll show you in class when the time comes. Okay. All right. So anyway, guys, this is just an introduction to the four wave behaviors: interference, reflection, refraction, and diffraction. You're getting ready to do an activity where you can play with those. All right. I hope this was helpful, and you guys have a great day.